All right. So in this video, I'm going to go over the contest 418, which, okay, well, I'm looking at the problems from this view. But yeah, so yep, this one, weekly contest 418. This is what I'm going to go over. I'm going to go over all 4 problems, and that's pretty much it. I think this problem will be interesting. My solution for this problem here, for the third problem, may be a little bit, I haven't checked other people's solutions, but um, the solution I have is like it works, but implementing it is a little messy. So, but I still kind of like it, and I'm kind of sticking with it just because I feel like it's a solution you can come up really easily if you're solving it. Okay, so the first problem is maximum possible number by binary concatenation. You're actually given an array that is of size 3. So you have 3 numbers, and you want to get the maximum possible number whose binary representation can be formed by concatenating the binary representation of all the elements and nums in some order. So this one, I decided the best order was 3, 1, 2, because if you concatenate those binary numbers, you'll get like this. So, I feel like this one's pretty straightforward. All you're going to do is just try every permutation, right? There's only 6 permutations, I think, here. So you just try all of them, and you try to concatenate the binaries, and you convert it to an integer, and you just take the maximum. So the code is very easy to do in Python. You just have a function, because the bin function will give you the binary representation as a string object, and then just, go through each permutation. You can use the permutation library in Python with the range of this to 3. And then, so this gives you 0, 1, 2, 3, and then you could just concatenate for each permutation and then get the max integer. This problem is a little more details. I'll go over this one in a little more details. So it's remove methods from project. You're maintaining a project that has n methods numbered from 0 to n minus 1. You're given 2 integers, n and k, and a 2D integer array invocations, where invocation is AI. BI indicates that method AI invokes method BI, which means you can say, since it invokes BI, you can draw that as a directed graph and draw an arrow from AI to BI. There's a known bug in method K. Method K, along with any method invoked by either directly or indirectly, are considered suspicious, and we aim to remove them. So what that means, since it says anything invoked by either directly or indirectly, given that K is a method, is going to be a node on this directed graph, so really it's just saying any node that can be reached by K, is going to be suspicious. Because it says directly or indirectly, so anything you can reach. So if I start from K, what nodes can I reach? And you can already kind of think, oh, well, I can use a depth first search or breadth first search starting from node K and just explore until I've explored every node that I can reach starting from node K, it as my source node. So you can kind of already see that element's going to be involved in solving this problem or an algorithm like that. A group of methods can be only removed if no method outside the group invokes any methods within it. Well, that's an interesting constraint here. So you can't have a node that is outside the group that you're trying to remove, the suspicious group, that is invoking that is connected to a node that's inside the group you're trying to remove. Return an array containing all the remaining methods after removing all the suspicious methods. You may return the answer in any order. If it is not possible to remove all the suspicious methods, none should be removed. And I give this example here. So you have the invocation. So 1 points to 2. You draw a directed edge from 1 to 2, you draw a directed edge from 0 to 1, and you draw a directed edge from 3 to 2, and you'll get a graph like this, and it says method k equal 1 is going to be infected. So what nodes can you reach from 1? Well, you start from 1, you search to 2, okay, that's all you can reach. So now 1 and 2 are marked as suspicious. Now the problem is you can't remove 1 and 2 because there are nodes 0 that point to 1 and 3 that points to 2. So there's a node outside of the infected group that points to it. So you can't remove anything. So you actually have to keep all the nodes. For this one, slightly different. So you have your invocations, you create the directed graph. And this time k is equal to 0, so that means what can 0 reach? 0 can reach 1 and reach 2, so all of these are infected. There are no nodes outside of the infected group which is connected to these nodes or can reach these nodes, so therefore you can actually delete them, and so the only remaining nodes will be 3 and 4. For this one, k is equal to 2. So k is equal to 2, so you take that node. What can you reach? You can reach 0 and 1, so all of these are infected. You can remove all of them. So I don't know if I need to really draw anything for this one. I think it's pretty straightforward. What you have to do, like just going through these examples, I feel like gives a really good sense of what you have to do. So all you really have to do is construct the directed graph and then create this thing that's going to keep track of which ones are suspicious, run the depth first search from the source node as k, and then you just run the depth first search. So every node that it can reach, you mark as suspicious. And you make sure you don't like revisit, you kind of cache it, or you don't, I mean, yes, in a sense you're caching, but the ones that you've already marked as suspicious, don't like continue searching through those or exploring. And then you just have your vector answer here. And then you can go through integer I equals 0 here and go all the way to n. And you say, if it's suspicious, continue. Otherwise, you can also go through int j and go through adjacency I. And then basically what you're looking for here is if you have a node that isn't suspicious, look through all of its nodes that it can reach directly. And if one of those is suspicious, then that means you found a node that's outside of the group of suspicious nodes that points to the suspicious nodes. So therefore, that means you can't remove the suspicious group. So in that sense, I set answer to n and I use iota, which iota will just iota is just a function in C++ that will allow it to go 0, 1, 2, 3, 4, 5, 6, all the way to n minus 1. Because I set 0 here, so it starts from 0. So this would just return all the nodes iterated from 0 to n minus 1, and then return the answer. And then otherwise, if it's not suspicious, you just add it to the answer. Okay. If it passes this test here. Yeah, you probably did it another way. Okay, so this is where it gets a little harder. Construct a two-dimensional grid matching graph layout. So you're given a 2D integer array edges representing an undirected graph having n nodes where, okay, I'm not gonna, okay, construct a 2D grid that satisfies these conditions. So the conditions you have to satisfy is the grid contains all nodes from 0 to n minus 1 in its cells, with each node appearing exactly once. Two nodes should be in adjacent grid cells, horizontally or vertically, if and only if there is an edge between them and edges. Okay, is guaranteed that edges can form a 2D grid that satisfies the conditions. Okay, so if we look at an example here, these are our edges. So if we look at the 0 node, the node label 0, 0 has an edge with 1 and with 2. So 1 and 2 have to be adjacent to it, which is the case. 1 has to be adjacent to 0 and 3, which is the case, and so on. Okay, your array, your 2D grid could actually be a 1D grid in a sense that it only has one row, in which case the adjacencies would be like this, and you just have to place them. It could be more complex. You can look at the constraints as well. You can see that the edge's length only goes up to 10 to the 5, and then it's like this. So the total number of cells in the grid is going to be 10 to the 5, or not 10 to the 5, but actually 50,000, which is what sets here. And it's guaranteed that the edges can form a 2D grid that satisfies the conditions. Okay, so for this one, because it's a little more complex, I'm going to actually draw out an approach that you can use. Okay, so this is an approach to this problem. Okay, you ready? So, all right, put this over here. I'm going to show some cases and then we're going to kind of build from it. So let's say you have one that's really just kind of one dimensional. So it's 1 here and like you could have 5 here or whatever. 0, 1, 2, 3, 4, the node labels, doesn't really matter. You can kind of think, what are some properties of the graph here? This is going to be a graph like so. And what you may notice is that the degree of this is 1, but the degree of anything inside is 2. Okay, so I'm gonna keep building up these patterns. Let's go to the next level, which is something where it has at least 2 rows, 0, 1. So we have 0, 1, 2, 3, 4, 5, 6, 7. So let's say we have something like this. Okay, so let's draw the graph that corresponds to this. So something like this. Okay. Okay. So this is pretty standard or straightforward as well. So basically, this is the corresponding graph, and you can kind of see. Well, you could count the degrees again, but this time these are 2, and the degrees of these are 3. So all of these are 3, and these are all 2. Okay. So you may be noticing is that the corner, like these are kind of, you could call these corner nodes. And in this case, the corner is here. The degrees are 1 and the degrees are 2, but the degrees are 1 less than the degree of every node that is not in the corner or an edge of the grid, however you want to say that. And you can call it an edge of the grid as well. Let's go to something a little more in depth. A grid with more involved here. So I'm not going to draw the graph. I think we can say, well, the graph is just this, right? But I think we can say what the degrees are. So the degrees are this. This one's a 2. The degree of this one's a 3, a 2. This one's a 2, this one's a 2, this one's a 3, this one's a 3. Okay, so again, the corner ones can be identified by the degree. This one's also a 3, this one's a 3, this one's 3, this one's 3. But the degree of these ones that are like inside are all 4. So we really have a degree that is 2, 3, 4 if the rows or columns are greater than or equal to 3. But we have a degree of just 1 and 2 if row and column is equal to 1. And we have one that's degree of 2 and 3 if R equal to or C if 1 is equal to. But really what we can think of them is like this, is the exception to this rule is really when you have a one-dimensional array. That's kind of the exception. But really you can think of these ones, like this is degree 2, 3, this is degree 2, 3, 4. But why is there 4? Because there's another type of grid cell in it. What I mean is like this grid cell, when you have a 2, 3, is something that is like this, right? In a sense, you only have 2 types of grid cells that I would identify. I would identify these as the corner or the edge of a grid. And I identify these ones as on the border of the grid or the boundary of the grid. So, and what you notice is the same thing here. These nodes that are on the boundary of the grid have a degree 3. The ones in the corner edges have degree 2. But these ones that have a degree of 4 are basically nodes that are not in the boundary or the edge. They are like internal, or maybe there's a better word for it. But yeah, that's just kind of the pattern. So really, these two cases are actually really similar, and then this is really maybe the only exception, where basically degree 1 represents an edge or corner, and degree 2 represents a boundary. A node on boundary, and of course you don't have any internals if you have just equal to 1. So given that, if you kind of break it down into those, if you break down the nodes into these properties, then what you can do is you can kind of realize that if I'm going to construct an algorithm, I'm going to kind of construct an algorithm that's constructive, and it has to start somewhere. So let's just assume it goes row by row. So it will construct the first row, and then it will construct the second row, and then it will construct the third row, and then it will construct the fourth row. The node that you pick for your very first element, you know is going to be in a corner and edge of the grid. So you know it's going to have to be, if you calculate the degrees, you know it's going to have to be a min degree. So you can pick any node that has a degree equal to the min degree. And then you start from that. And then that kind of sets your seed in a sense. Like it's kind of like your seed, like a random seed. You give a seed and it will, this is probably a bad analogy, but if you give it a seed, from my understanding, it will change like the randomness. It's kind of like seeding it. It's like, I actually had 4 options to start this corner, and I just chose one, and now that's my seed, and I'm just going to keep growing, just like a tree actually too. I just keep growing out from it based on what is attached to it. Now, if you think about it, here though, if I start from this one, I seed it with this one, I start with a 0. What element do I pick? Because I'm going row by row, right? What element do I pick for it to be adjacent to it? It doesn't actually matter, right? At this point, I could pick a 1 or 4, technically. They both are attached to it, and there's no constraint on it, so I just pick that one. So, I just picked the 1. Then I just need to pick what is adjacent to the 1, but is like this. The only constraint here is you have to make sure that the degree represents a degree of a boundary, which means the degree of a boundary is 1 greater than min degree. So that's what I'm going to say here. So this represents an edge, not that kind of edge, but an edge on the grid, a corner of a grid maybe. And then boundary ones that are going to be min degree plus 1. And then you have internal ones, which are going to be min degree plus 2. So then if you go back up here, and I just think about this, so I know I'm on the boundary. So how do you can know you're on the boundary, but also there's 2 properties. Like this 1 technically connects to the 5 and it connects to the 2. So how do you know which one to use? Because you want to consume the boundary one first, and also you want to consume the boundary one because you're in the first row, So you have to consume a boundary one. So you kind of know it's the 2. It's not going to be the 5 for sure. So it's got to be the 2. And then here, this is the last one. So 2 connects to 3 or 6. Well, you're not going to use the 6. You're not going to use the 1 because you've already used the 1. You're not going to use the 6 because it's internal. You're going to use the 3, and that's going to be a corner. So then you need to somehow tell it that, hey, this is an edge. So it needs to start a new row. And so when it starts a new row, it's then going to start with the nodes. It doesn't actually have a node, so it needs to find a node that it can use. So it goes back to the node up here. So let me draw this out again so I can do this. Okay, so when it's at this node, what is it going to do? Well, the row is equal to 1, so the row is greater than 0. What it's going to do, and also since the column is equal to 0, it needs to look at what is above it. So it needs to look at the grid because you've already assigned the first row. It needs to look at what node is there in this and above it, and then it uses that to pick the node there. Because like what's attached to the 0? Oh, it's a 1 or a 4, but it can't pick the 1. The 1's already been picked, so it has to pick the 4. So okay, it places the 4 there because of this reason. And then okay, when it does the 5, how does it do the 5? Well, okay, it's going to pick whatever is adjacent to the 4, which is either 4 or 8 or this. But what you can kind of do is you can kind of say, well, you know the row is greater than 0 and the C is greater than 0, but also the C is not equal to like this boundary, which represents C minus 1. So you can kind of like, you can kind of find that you can find the number of columns when you develop the first row. So you can kind of make sure that it's not on a boundary. So you kind of say it can't be the 8 because um, because I can tell I'm in an internal position in the grid. I have enough information to know I'm in an internal position. So yeah, so then we'll go to the 5. And the 5, same thing, it's in an internal position. So it could pick the 9. It actually really doesn't matter, but it's going to pick the 6, right? And then the 6 can pick the 7. And so the 6 could pick a 10, but this time it's not going to pick the 10 because it's going to say, hey, my column is at the boundary, which you found when you found the first row. You found the length of the boundary. So then it just goes down here and it follows the same logic. It uses the same thing. 4 is attached to 5 and 8 and 0, but 0 and 5 have already been used, so it has attached to the 8. And then the 8 attached to the 9, and then so on and so on. Then when it gets down here, it's like, what's attached to the 8? Well, only the 12 is left. What could be attached to the 9 and the 12? Only the 13, and so on and so on. So yeah, so that's how I did it. Now the implementation is a little bit messy because it has to deal with it. I may have, let me just go through it. So here you have the JC list. I use an unordered set. That way I can like remove nodes that I know have already been visited. And you calculate the degree. So first thing is you calculate the degree. You get what the min degree is, which is going to represent the edges of the grid. And then you want to find a node, your seed node, which is my U here, which is going to be when the degree is equal to min degree. And then you initialize your row and your column to 0, and you initialize these the uppercase R and uppercase C, which represent the size of the grid, which you don't actually know what it is yet. So that's going to be worked out. But you kind of build the grid here because you're going to kind of construct it on the fly. And n is just the number of nodes I have to place. So the first thing you check is if R is equal to grid.size, that means you need to start a new row. And then you're going to push back U. So whatever the node is right now, that's going to be the node added to this row. Set the degree to 0. That's a way of actually tracking that you've already used that node. And I'm going to track if it's a corner or an edge, and I'm going to track this stuck, which I'll go into why that's there in a minute. So the first thing it's going to look for is this. It's going to loop over the nodes that are adjacent to V. And if a node's already visited, it's set to 0, so it's not going to be equal to min degree. But the first thing it's looking for is basically nodes that are not equal to the min degree. So, well, no, sorry. I don't know. I read this and I wasn't thinking. No, this means that the degree is not equal to min degree. It continues, so it skips any of those. So it's looking for a node where the degree is equal to min degree. So this is where it's trying to find if there's a corner node. But it also needs this logic here, which is just checking that if we're at a row that is greater than 0 and we're at a column which is less than C, then we need to check the node above it and the node above and to the right of my current position, because when I put a node there, let me just draw what this means. So what this means is that I'm at this location and I'm trying to determine what node I can place here. So I have to look up here, which is R minus 1, but C plus 1. Okay. I think you can do that differently, but that's just how I implemented it. And then you update U to be this corner, and you say this is a corner, and you say it's not stuck, and you break. And then it won't do anything if it's a corner, and it won't do anything here. And it'll increment the number of columns. And if it's the first row, it's going to use this to set the number of columns that are going to be fixed for the rest of it. And basically, if it's a corner, so basically, if my next node is a corner, or it just checks if r is greater than 0, it's like a boundary, but on all the way on the right side, so you can't continue. It's going to set the degree to 0, and it's going to push back this node, decrement the number of nodes I have to place, and then it's going to set out and figure out the next node to start the next row. So it increments the row, sets the column to 0. It gets the node that's right above it, and then it determines what's node I haven't visited that I can use, that can be used next. It doesn't have to check for some degrees because for that position, it's a node that's here, right? You're trying to figure out what node to put here, which means any node here is only connected to these nodes. And, what if it accidentally, or the 0 is only connected to these nodes. The 4 is only connected to these nodes. So when you're trying to place the 8 here, everything that 4 is connected to has already been used. So this is the only node that hasn't been visited yet, right? So let me do that again. So let's say I'm trying to figure out what node to put in this location. I look above it, I look at the 4, because I want to start this row. I look at the 4. The 4, it has 0, 5, and 8 connected, but 0 and 5 are already visited, so those degrees would be set to 0. So we'll ignore those, and it'll only add the 8. That's essentially what that will do. And then if I go through other possible cases, which is, this is if it finds a corner. If it doesn't find a corner, it's going to try to find a min degree plus 1, which means it's trying to find a boundary node. That's the next thing it tries to find. So in a sense, there's a greedy order here. You look for corners first, an edge first, and then you look for a boundary, and then you look for just an internal one. But basically the logic of this one is similar to the one above. So it does this thing here. Again, it's figuring out what the next node is, and it's going to say stuck to false because it's not stuck. If it was stuck, then you're just going to look for any node. That means you didn't find an edge node. You didn't find a boundary node. That means it's looking for an internal node. So it just kind of goes through here. Oh, okay, sorry. I said I used this unordered set so I could remove from adjacency list, but to track visited, but no, you track visited by setting degree equal to 0 for that node. The unordered set was just used so I can use this contains function actually, because I needed to check if it was adjacent to to this element. And then this one will check if it's stuck. That means it has no boundary, has no edge node. It's going to go through and just find if there's anything it can use, and then use that. So that'll pick the internal node. So to explain the order of this, let's do this. So why do we look for edge nodes first? If I'm in this location and I'm trying to figure out what to put over here, why would I look for edge nodes first? Because I think because of this reason. This too, if it's connected to an edge node, it's not connected to a boundary node, right? Like if I draw this out here, 3, 4, and so on and so on, right? And like I'm at 3, right? So for 3, it's not connected to an edge node, but it's connected to boundary nodes. And if I'm trying to figure out what to put over here, it's going to use the 4 because the other boundary node's already been visited. But if I'm at the 4 here, and let's say it may have like this. Like let's imagine this is just a 2-dimensional one. So it's just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 here. Okay. So just imagine it's like this. The 4 is here. It does have a boundary node, node 10, that is unvisited, but since it's connected to an edge node, it places that one first. That way, it finishes off this row, right? Like you can't not place the 5 here, because if you chose the 10 here, then you still have the 5 to be placed. And well, the 5 is only going to be connected to this other element, 11. So yeah, so I don't know if that's the best explanation or it makes sense, but yeah, I mean, roughly that's how I did it. So you place boundaries first, and then you place these, these, you place edge node first, then you place boundary, and then you place internal if you have no other option. I think that's what makes it a problem hard, actually, is determining that that's true. Okay, for this one, sorted GCD pair queries, I will go into depth on this one because I think it's interesting, and I think it's really hard. You're given an integer array nums of length and integer array queries. Let GCD pairs denote an array obtained by calculating the GCD of all possible pairs. For each query, you need to find the element at index queries I and GCD pairs. Return an integer array answer, where answer I is the value at GCD pairs queries I for each query. And the term GCD AB denotes the greatest common divisor of A and B. Okay. It's kind of weird, but looking at an example, you have this number array and you have these queries. So if you take your number array and you generate every possible GCD pair, which is this here, you can do 0 with 1, 0 with 2, or 1 with 2. You get 1, 2, 1. If you sort it, these are your GCD pairs. And then you run your queries in there. So the queries just represent the index in the GCD pairs. So here you have 4. So obviously this is like, how many ways can I pick 2 elements from here out of all 4? So it's like, how many ways can I pick 2 out of 4? And it's like, oh, there's 6 ways to do that. So is the number of GCD pairs, and you can calculate them. Okay, so you can see that the number of elements is 10 to the 5, but you can also see that the largest value in nums I is 50,000. That's going to come up later. That's like just a little under 100,000. So this will come back. But yeah, the queries can go all the way up to n times n minus 1 divided by 2, which is just the formula for the number of ways to pick 2 items out of n items. So it's combinatorics. So yeah, so brute force solution would be just to generate these GCD pairs in O of n squared time complexity, but that's not going to be fast enough. So you have to think of something else. The main thing that I think of in terms of GCD is really breaking down the integers into their prime, the prime integers. Every number can be broken down into a prime integer. So it can be broken down into like a set of prime integers with some power for each one, like because 8 is 2 to the third. So it's 2. 2 is a prime integer, but it can be used 3 times. So you have that there. You have that fact. So you're kind of looking at a number theory problem here. You're kind of looking at kind of just figuring out, okay, I gotta erase this first. I want to clean slate. Here we. Yeah. So basically, you can do this. Okay. So let's do this. So what you can do is you can think in terms of number theory. You can think of like how to represent numbers. Like 6 is 2 times 3, and we just say the power or something. The reason why you might do that is because, like, let's say you had 9, which is 3 squared. So the GCD of 6 and 9 is actually equal to 3. Why? Because 3 is shared between them. So if you say, oh, 2 times 3 and 3 times 3, well, this 3 is the most number of primes that are shared between them. So, okay, it's that. Okay, fairly enough. There's more details about it, but in a sense, we can say something, we can also view it like this. So I want to calculate the GCD of two integers. Those integers can be represented as a set of elements where you have your prime integer and then some power, and it can be a set of these how do I do the set notation? I don't know, just say P is an element of this. I don't know. Yeah, so anyways, where, oh no, I think I got it. Where P, or let's say this is the factorization of x, let's say, or this is the prime factorization of something like x is equal to this, as long as x divided by p, yeah, as long as this is equal to 0, that is x is divisible by p, then you can do that, I guess p to the I. So that's kind of represents the prime factorization. So what you can say is, you can say I have two of these sets. So I have a set for A, and then I have a set for B. And if that isn't clear what I'm doing, let's say A is 2 and, or no, A is 15 and B is 20. So A here would represent 3 and 5, and B here would represent a set of 2 and 2 and 5. Okay. So, I mean, in a sense, this is like 2 to the 2, by the way, is what I'm doing here. So yeah, you're trying to take the, but yeah, it's just the set of prime integers. Yeah, let's just say that. This is just the set of prime integers. Maybe this is how I wrote this math notation is kind of weird, but it's just a set of prime integers that, the prime factorization of A and B. So the GCD of A and B is actually equal to the product of the intersection. So I think you can represent it like this in set theory. It's actually the product of the intersection. And that's literally what GCD is equal to. If you're looking at the prime integers of the GCD, you can just say the prime integers of the GCD, let's say G is just A intersected with B. So you can also say this is the summation or product of that. So this is a true statement. So, okay. So the reason why I'm showing that is really because there's something we can say here, okay? Let's take some examples. Let's take an example where I have two elements. Let's say A is 6, and say B is 12, okay? So in terms of this, if you take the GCD of 6 and 12, you get 6. You also know that the sets of these are 2 and 3, and 2 and 2 and 3. So, you get the 6. So if you take the intersection, you get 2 and 3 as an intersection, all right? So if you're saying, like, if you're counting this, you say, okay, yeah, that makes sense, right? But you can also say that they share a 2 and they share a 3 as well. So they share a 2, they share a 3, and they share a 2 and a 3. So let's say you have the count of this. If I have the count of this, the number of ways this can happen, and then I have the count of the number of ways this can happen, number of ways this can happen, what I have to say is that, like, there's like an inclusion-exclusion principle here. I don't know exact details with this representation, but here's a representation that I understand, I guess, for this one. is you're going to use the fact that the numbers are only up to 50,000. And the first step I want to do is take all the numbers in the array and count the number of divisors. So an example they have 4, 2, 1. So if you count the divisors, 2 is equal to, the first thing you do is you pre-compute these divisors. That is, given an integer, given x, you need to have a list of divisors, which just means that like 10, the divisors are 2, 5, and 10, I guess, if you include 10. If you have something like 8, the divisors are 2, 4, 8. So, if you include all the divisors. So those are all the divisors, right? So, okay. So then what you can do is if you pre-compute all these divisors for everything, then if you loop over the numbers, so given 4, 4, 2, 1, you loop over these numbers, and you can count the divisors. Like I can say, what are the divisors of 4? It's going to be 4, and then 2, and then I guess you count 1. I don't know. What are the divisors of this 4? Okay, so this, same thing. What's the divisors of 2? It's these. What's the divisor of 1? It's this. So now you have a list of the count of divisors for all your numbers. So you've converted these numbers into just the count of their divisors. So then what can you do with it? Why is this useful? Because you can look at this very quickly and you can say, in terms of my GCD, I have 2 numbers that have a divisor of 4. So you think for certain I have a pair where the GCD is equal to 4, right? And which makes sense because you have GCD 4, 4, and you get 4. I mean, you have 2 numbers with this, so I can achieve that pair, right? How many GCDs are equal to 2? Well, you might say, okay, it appears in 3 numbers. So you might say, how many ways can I pick 2 from 3? 3 ways. So I say, okay, there's 3 pairs, or the GCD is equal to 2. However, this is not correct. There's actually only 2 pairs. It is 4, 2, and this 4, 2. The reason why it's not correct is because these 4 and 4 share a divisor of 2, as well as sharing divisor of 4. That is, they share a divisor of 4 and they share a divisor of 2. So it's overcounting them. It's counting them again when it shouldn't. I guess, okay, so that's the thing that I was trying to show up here. I had forgotten, it had been too long. Was with this 6 and 12, I was going to try to show is that if you take the divisor that they share, it's the 6. They both share a 6, but they also both share a 3, and they both share a 2, and they both share a 1. So in this sense, you'll count the GCD as 6 here, but then you don't want to count the GCD as 3 because they both had a larger one. So you have to make sure you subtract those. So I'll show this example. So again, there were 3 pairs, but we know there's only 2 pairs. So what we have to do is we have to go through the multiples of 2. That is like, so say take 2 and take the multiples of 2. So take 2 times 2, which is 4, takes 3 times 2, which is 6. But these don't matter. But like these are other ones I could share. So the 4 one is interesting because we already know there's 1 for that. So given that there's 1 pair for that, and we know that one of the divisors of 4 is 2, that means we already counted it. So we want to subtract that. So if you were to subtract that, then you would only count 2 here, and you'd count 1 here. And then for the 1, it looks like there's it looks like, yeah, I did that. Didn't even realize. Okay, it looks like for the 1, there's picking 2 from 4, which is 4 factorial over 2 factorial, 2 factorial, which is 3 over 2, which is 6. So it looks like there's 6 ways, but we know that there's not 6. There's only 1, 2, 3 actual GCD pairs. So what you have to do is you have to look at 1, you have to look at 2, and then look at 4. And you already know there's 1 pair for here and 2 pairs for here. So you know it's counting those in addition to counting the 3 here. Because it's also counting that these and this, or sorry, it's also counting this and this and this because they also share that divisor of 1. So it's counting these pairs as well. I could write them like this. It's counting this pair, and this pair, in addition to counting this pair, and this pair. So if you subtract out these, then you'll get your answer. So you're kind of just doing this over counting and then doing this correction. Yeah. And it's related to the inclusion exclusion principle, but this is like a good example of it in practice. If I say something more general, like let's say something. Let's do something more general. So let's say so first off, from the above, you know you're in a loop over divisors from largest to smallest. So one thing I'm going to say is, like, let's say you have you're taking a divisor D, but let's say the count of this divisor is equal to 1. What does that mean? That means that maybe the divisor is 20. And so maybe you have an array where you don't have a number that's 20, and you don't have any numbers that are multiples of 20, right? You don't have a 40, you don't have a 60, you don't have an 80, you don't have any numbers that are multiples of 20 either. So you have no number that shares the 20 divisor. There's only 120 in the array, and there's nothing bigger than it. So there's no way you could ever have a GCD pair with the 20 because it stands alone. The only way you could have it is if you had some multiple of the 20, where the GCD could be 20. But yeah, you don't have that here. So if the count is 1, you can ignore those. Those divisors are not going to contribute to a GCD pair. But if the count is okay, so my battery is dying for my headset, so I don't know if I have time to do this. Okay, so so you get this count of the divisors such as D, and then I think so yeah, so again I did the 20 example, like if that was just a single integer and it was count that you see. So if the count is greater than 1, that's when you can start like forming pairs with it. So if the divisor is 20, let's say still, but let's say the count is like, I don't know, like there's 4 of them, right? Well, how many pairs can you form is 4, pick 2 from 4. So all of these can potentially be formulating a GCD. So there's 6 of these. So potentially 6 of these could be creating a GCD. The only reason they would not is for some reason, let's say you have 2 numbers that also have a divisor of 60, because that means that this pair, you have at least one pair where it's a multiple of 20, but it's a greater number, which means that this would actually be the GCD of this pair. So you just have to go through and subtract off those previous GCDs that are possible. So it kind of corrects for the overcounting. And hopefully this is clear. I feel like I did. I think I covered most of the details To implement this, a few key things is I'll come back to this pre-computed stuff, but I'll just go over real quickly what this part does. Is just calculating for each divisor. So it's going through each integer here of y, and then going through each of the integers that can be divisors of it by just incrementing by x. So this should work in about like I think n log n time complexity. So okay, and then here I get the max element. We get the diff count and we get the GCD count. Just use memset. Memset is really fast at setting all this to 0. And use an unordered map for the frequency. So you look at the numbers and you just calculate the frequency. And then for each of the numbers in the frequency, go through all the divisors of each of them and increment by the frequency. That is like a number you could see it multiple times, like 3 times. So you want to increment each of its divisors by 3. So this will count your total divider, sorry, divisor count throughout all the array. And then here I'm going to generate my GCD value. So again, if the div count is less than or equal to 1, you ignore it. Oh, and you start from the max value, and you're going to go until 0. Otherwise, you calculate how many ways you can choose 2 from the div count, and you say, okay, well, that's how many GCD count there is. Then you have to correct for it because this will overcount. You have to look at every multiple of the GCD value you're considering up to the max. So you can do that with this iteration here, and then subtract whatever the GCD count was for that, because you don't want to count that one again. And just implement all these into the GCD val. So track like all of these. Reverse this because this is, you want to sort it in ascending order. And then you have the prefix sum here where it's just going to calculate a prefix sum across the GCD vowels. I guess this part I didn't explain. But yeah, just do the prefix sum and then the answer. So the query will, how it will work is it'll query the prefix sum. So yeah, let me explain this part, because at this point, basically you built this prefix sum up. Let me just go in a little more detail about this one. But essentially, if you had that example where you have the 4, 4, 2, 1, so you have your GCD pairs are 1, 1, 1, 2, 2, 4. And so your prefix count here would be, this would be your prefix count. So it'd be 3, 5, 6. And your GCD values would be 1, 2, and 4. Oops, I didn't do that. And then this would be your prefix sum. So this is just the count of these GCD values incremented. That way, if you have a query, so if I query for, like a basic query would be you're querying for, I think the last one, which would be, I just need to check, it's 0 index, right? Yes, it's 0 index. So the last one could be, okay, so the last one could be uh, the 5th index, because you have 6 elements. So that if you query 5, then it needs to find this element. This is the answer. If it queries for 4, the answer should be 2, right? Sorry, we can look up here to actually see why. 0, 1, 2, 3, these are the indices. So the 5th index, the 5th query should return 4. The 4th query should return 2. So if it queries the 4, if it binary searches for the 4, it needs to return right here, okay? If the binary searches for 3, 3 should return 2. So for 3, it should return here as well. So what you can do is you can use lower bound if you just like, there's another way I would show this actually. If I just show an array here, where I show here, 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 1, 2, 3, 4, 5, 6, like this, and then what I can do is Um, what I can do is say the answer here should be 1, 1, 1, 2, 2, 4. So this is querying 0, 1, 2, 3, 4, 5. But if you look at what's associated with what, 1 is associated to 3, 2 is associated to 5, 6 is associated to 6. So if you look at this here, you'll find this if you query, or if you in the prefix sum, that is, you have to make it work with the prefix sum, which is like this. So this range right here, it searches 3 or 4, it needs to return 5. So what you can do is you can just add 1 to this. So if you search 4 to 5, that will binary search to the 5 here with use lower bound. If you're binary searching for 5, just add 1 to it, and you binary search for 6 here. And then here you're binary search from 1 to 3. So yeah, hopefully that's clear.